a finite state machine is a model of a system that has a finite number of states and behaviors associated with those states. And then we also have transitions to determine when that's the other. And in fact, what you're seeing here is one of these discovery pages that sort of explains the concept of what finite state machines are. And so these are great for modeling complex control logic or decision logic.
Yeah, so I think if you could map that to a real world problem, right? Let's think of I don't know, a car driving or something, and you've got something like an automatic cruise control, right? So it's your state machines or your state logic that's sort of controlling when it shifts between the different modes within the automatic cruise control controller. So an automatic cruise control essentially works in the way that if you're close enough to the car in front of you, you'd sort of hold your speed and maintain that particular distance. But if that distance increases beyond some threshold, you can actually keep, your car will exceed the speed that you have set for it in order to make sure that it meets that distance. So essentially, your system has a finite set of modes of operation, and you can use state machines to model that, right? If that's one way of putting it.
Exactly. And so now that we have some basic understanding of what those are, let's take a look at what are some of the tools that you have available to build them, model them, and ultimately implement them in the real world. So today we want to focus on Stateflow. And again, this is the software or the product for modeling and simulating decision logic with state machines and flowcharts. So it really gives you those, these elements so that you can build those flowcharts, straight transition tables, truth tables pretty easily. And the great thing is Stateflow works with both MATLAB and Simulink, but today we're going to focus on Stateflow for Simulink users. So if you're interested in Stateflow for MATLAB users, let us know in the comments below. So, so far we've covered state machines, Stateflow, and I think we can infer that Stateflow is great for developing supervisory control logic, task scheduling, fault management applications, and other things like communications protocols, user interfaces, and much more. Okay, so this right here, what I'm showing is the product page of Stateflow. You can come here and sort of explore more. What are some of the things that you can do? And just to give you an idea of where Stateflow fits with MATLAB and Simulink, for those of you who are not too familiar, I want to show you this slide, right? We have MATLAB, which is the programming environment for numeric analysis, numeric computations, and much more. Simulink, we also have a live stream on that, is the platform for modeling dynamic systems. And this is a graphical or low-code environment for modeling and simulating those dynamic systems. And then we have Stateflow, which is an add-on that, again, works with both MATLAB and Simulink. And in fact, we have over 100 add-ons that help you do specialized tasks more easily.
For everything, right? There's a toolbox for everything.
Yeah. All right. So now I think we answered the first question. What is Stateflow, state machines, and so on? We have a little bit of background and context. Let's jump into some examples. So let's tackle a real world problem. And let's think of cell balancing. Let's imagine we have a battery pack. Maybe this is the battery pack that you would find on a hybrid electric vehicle. And so as you cycle this battery pack, that eventually causes the battery cells to go out of balance. And what that means is that you end up having cells with different SOC levels or state of charge levels. And that's undesired because the weakest cell, or the one with the lowest state of charge, that limits how much of the battery you can use. And the strongest cell determines how much charge you can put into the battery. So that's undesirable. And so we want to go from something that looks like this to something that looks more like this, where all of our cells are in balance. So that's the problem that we're trying to tackle here. So let's jump into the product. To access Stateflow, I can do that. We're going to focus on Simulink today, so I can access Simulink from the start page. And to get to Stateflow, I can create a blank new model, or I can start with templates for Stateflow here. So this is the nice thing with the start page, that I get a few templates for blank charts, simple charts. So those give you a starting point. I already have a model that I put together to tackle this charge balancing problem. So let's use that as a starting point. So what I have to the left are the inputs of the model. Here I have the BMS state. So this is associated with this switch. And these are dashboard blocks that allow me to interface with my model or interact with my model. So this BMS state is just a switch, right? On, off, 1, 0. Here we have the cell voltages. So this is an array of values that are associated with these knobs so that I can change the voltage values. And then from there, we're just taking the maximum and minimum cell voltages. And then on the output side, we're looking at the balancing command for each one of the cells. Okay, so our challenge is to build a state machine that looks at all these inputs, determines the operating state of the system, and then gives us a command or an output based on that, right?
So it's essentially the brain of your charging system, if you could
exactly.
Think of it that way.
That's one way to think about it. So, well, there's a couple ways that I can get started here. I can go to the library browser. We have videos doing this before where you can explore all the blocks and libraries that Simulink gives you. Or I could just use quick insert. So I'm going to go and type Stateflow here. And it recognizes that I'm trying to find a chart from the Stateflow library. So I just select that. And here is my chart. So now I'm going to make connections first, and then we'll worry about beautifying the model. So I'll make this BMS state connection here. And you notice that I can just create ports by clicking and dragging. And then it's really nice that these ports are automatically named after the signals. And I can even edit those port names as I create them. So let's continue making these connections here. And now I'm going to connect the output here, the balancing command on the output side. And now the tool strip gives me some really nice formatting options to match the size and align that area in my Stateflow chart. So that's where I want to have things. Now we're ready to jump into the Stateflow chart and start building the brains of our supervisory logic or of our state chart. So one thing I want to bring up is, the tool strip. It shows me different capabilities based on what is available for Stateflow. So if I go into this debug tab, I'll see things that are specific for Stateflow, same in the modeling tab. So I want to bring up this symbols pane because this is pretty important because this will help me understand what are the inputs, outputs, data, and parameters that I'm working with in my Stateflow chart. All right. Now, that's the symbols pane. Here I have my panel. Again, this panel is a collection of dashboard blocks. And when you make them a panel, they come with you to different levels of the model hierarchy. So pretty useful for modeling, testing, and simulating your model. The nice thing is, while I don't need it, I can just double click it and minimize it so that it's not in the way while I build my model.
This was a relatively new feature, right? I think it was added, when was it, 20A maybe?
A couple of releases ago, yeah, probably
Yeah.
20A, I think. So yeah, pretty nice. And you can have multiple tabs with the panel too. So it's not just one tab. You can change multiple inputs, even look at the outputs in the same panel. So it's pretty nice. So let's start adding a state. So you could add elements here with the tools that you get on the left, or you could also use quick insert. So here, I'll just start typing in the canvas, and I want a state. So let's select that. And here I have a state. And here you also notice this dark dot at the top. That's the default transition. So when the Stateflow chart wakes up and starts executing, that's the first point that we're going to go to. So I want to name this first state balancing off, right? Our operation is basically off. Now I'm going to create another state. So I can just draw and select state. And this one is going to be balancing on. So now we have these two states. And now we need to define transitions to go from one state to the other, right? So I could just draw lines here by dragging the edge of the state. And the transitions to go from one state to the other can be events. They can also be conditions, or they can be actions that happen as those conditions are evaluated. So I'm going to go with the square brackets since those are conditions. And the condition here to go from off to on is that the BMS state has to be equal to 1. If you remember, the BMS state is the switch that we're using in our dashboard panel. So now to go from on to off, you guessed it, I want another transition that is probably just the opposite, where BMS state is equal to 0.
So I think a quick thing that we should point out here is essentially every transition has three components to it. You either have an event, a condition, and an action, right? So we haven't really gone into events. We'll go into events a little later in the stream. But I think the one thing that we need to point out here is every time you put something within a square bracket, it's a condition. Those are typically inequalities or Boolean type expressions that you want to have. And the term that we use to call conditions, we say conditions guard or conditions guard transitions, if that makes sense. So as soon as your program enters the state, it's looking for that condition to be true so that it can take that transition and go to another state. That's just sort of a high level understanding of what's going on here.
Yep, those are excellent points. So now we got states, we got transitions. We need to determine what happens or define what happens when I'm in one of the states, right? And so the way we do that is with actions. And in Stateflow, you can have entry actions, during actions, and exit actions. And so you can have them individually, or you can even combine them. And so the names are self-explanatory. Entry actions happen when you enter a state. During actions happen while you're in a state. And exit actions happen when you leave a state. In this case, I just want to use entry and during actions. And the first thing I want to do here is I want to set the balancing command. If you remember, that is the output that we're working with. I want to set that to false when I'm in this state, right? Balancing is off, nothing is happening. Probably just copy that. And then in the balancing on state, I also want to establish entering and during actions. Now, a nice thing is that I can abbreviate those actions with just the first two letters. So there's a little tip. And so I want my balancing command to be true. All right. And so I think at this point we have some basic logic that we should be able to simulate. And if we look at the symbols pane, we have the outputs, the inputs, and these three things that are not being used yet. So those are the warnings I'm getting here. But I think we're ready to try a first simulation. So it's going to compile. And then as we start running this, you'll notice that this is going to come to the default transition, and it's going to should go into the balancing off state. And one of my favorite things about Stateflow is this animation that helps you visually understand what's going on and debug at your complex decision logic.
Yeah, so it's essentially it'll light up whichever state the code's in at that point, right?
Exactly. Yeah. And so another nice thing is that when you hover over states or transitions, it gives you some information on the data that you're working with. So pretty nice. Okay, so we're in this state. If you notice here, our balancing command, the value is 0 right now, as we would expect, as false. If we flip the switch here to go to on, we evaluate that condition, and that becomes true. And now we're in the balancing on state. Therefore, our output is 1. If I flip the switch back to off, yep, we go back to off. And so we got some working logic.
Some elementary logic that's in place, and we're ready to go.
Exactly. So I'll get my dashboard out of the way, and we can continue adding a little bit of complexity as well. So now let's imagine that we want to compare the individual cell voltages to a target delta voltage. And for those cells that are out of balance, then we're going to send them an individual balancing command. So let's think about how we could do that. And so I want to start by calculating a delta cell voltage. So this is a new variable here. And that's just the difference between the maximum cell voltage and the minimum cell voltage. And you remember, these are inputs that we're working with. This is a new variable that we're working with. I'm also going to use that in this state, the balancing on state. So we know what the delta cell voltage is at all times. And I also want to use this delta cell voltage in my condition. So the nice thing is that I can combine logic with these transitions, right? So I can just say, and we want delta, or whenever delta cell voltage greater than, let's say, 2 volts, this could be a parameter or something. I'm just going to go with 2 volts. If that delta is greater, then we'll transition here. Exactly. All right. And the last thing we need to do here is we need to determine the balancing command for the individual cells. So what we'll do here is we're going to look at the cell voltages. So that's the array of values that we have. That's one of the inputs. And we're going to compare that to the minimum cell voltage, so to the lowest value. And whenever that delta is greater than 2, so the threshold that we're working with, then we'll send a balancing command to those cells, right? So we just added a little bit more complexity here. And so if we look at the symbol pane, this is another thing that tells me if I have a typo or not. So I know this is an input, but right now it's not resolved, so I got a typo there. Thank you, symbol pane. And then this one is an undefined symbol. So all we need to do here is just tell Stateflow, hey, this is local data, right? Because this is something that is being calculated in the chart. And now all of our symbols are resolved. So we have, now we can simulate our logic and see what happens if it breaks or if it works. So when we run it, fingers crossed.
It's always fun doing live demos, right?
That's the best part.
Plug
All
it
right,
play.
It's working. So we started the balancing off state. Again, the output should be an array of zeros, right? Because they're all false. And we can double check that if I go out here. Yep, they're all zeros here. You can see that in the display. Now, if I flip the switch, now I have one of the conditions to go into the balancing on state. But you see that the delta cell voltage is only 0.3 volts, right? And so we need it to be more than 3 volts. So now I can change the voltages in the cells here. In reality, you might have a physical system that is giving you sensor feedback on these voltages, or you could have a plant model that gives you feedback on these voltages. Here, we're just going to do it by hand and change the voltages for cells 1, 2, and 3. So you'll see that when I start changing these values, then the delta cell voltage became like 7 volts, and therefore we have all the conditions to go into the balancing on state. And so if we look at the outputs now, I go out one level, you see that we're sending a balancing command to all the cells except the lowest value, because we're implementing a passive balancing method here. So we're trying to discharge all the cells with the higher state of charge down to match the lowest state of charge, which is cell 1 in this case. So, this is a functional logic that you could apply in the real world, and it just took us, 10 minutes to build this. And so the alternative would be to program this with a bunch of
switch cases,
else statements. Yeah. And so you could end up writing hundreds or thousands of lines of code, whereas with Stateflow is just, a chart that makes it really easy to create these state machines, debug them, and analyze them. And so now let's see what happens if I turn off the switch, right? Because this condition should actually take over. And so if I switch it off, then there we go. We end up back in the balancing off state. And as you would expect, our commands are 0 again. So that is the first example of how to build some cell balancing decision logic with Stateflow.
Yeah, I think now is a good time to stop and take some questions while we do some technical settings in the background, so we can show you another example on how to fly quadcopters with using using Stateflow. So I'm just going to look in the chat to see if there are any questions. We have a question on integrating Stateflow with AutoSAR. This one's interesting. So Ed, do you have a good answer for that?
Integrating. Can we share more details?
Yeah, I think so. So my understanding of AutoSAR is a programming construct or a programming standard that you have to sort of meet align to, and I think for the most part, Stateflow charts sort of make up the larger Simulink environment. So if you in the realm of a Simulink model, a Stateflow chart is just another Simulink block, if you will. So as long as you can sort of get your model to work within within those AutoSAR constructs, it should just work. But there's definitely a lot more information in the documentation. I think that's out of the scope of this webinar, but you can take a look at the AutoSAR block set in the documentation to sort of go through that.
Yep, that's a good point. Any other questions coming up?
I don't see, is this clip going to get saved? Yes, you can actually watch the live stream after it's done.
All right. If we go back to the previous example that I was covering, can you explain why the cell balancing command is being set to the cell voltages minus the minimum cell voltage divided by 2, or greater than 2, I'm sorry. So what we're doing there is comparing the voltage of each individual cell. We're comparing that to the lowest voltage in the array of values. And if that's greater than 2 volts, and again, it could be any number, that's just a threshold that we're working with. So if that delta is greater than that, then that cell needs to receive a command that we need to balance it. So discharge it to match the lowest SOC that we have in the pack, or the lowest voltage that we have in the pack. So hopefully that makes sense. Again, this is going to be recorded, so feel free to go back, rewatch the explanation, and look at the code so that you understand what's going on there.
And then we have another question saying, is Stateflow obligatory to be a part of the control system model? I don't think it's obligatory. I don't think it's a necessity. It's a nice to have. The way I like to think of it is you have some sort of PID or MPC or whatever low-level control that's controlling the actual actuation of motors and things like that on your system. Stateflow sort of acts as the high-level controller. So it's sort of generating those control commands that would go into your PID controllers, if you will. So I don't think anything's a necessity. It's just Stateflow is a nice thing to have to control the high-level decision logic of your system.
Right. It's a choice that you get to make, right? If you implement this kind of logic, again, with C code or just plain text code, you're going to end up with hundreds, thousands of lines to handle all the complexity, when you start developing things, large systems. Whereas with Stateflow, it's really intuitive to create this graphically, to debug it, to analyze it. And that's one of the benefits that you get, right? In addition to the automatic code generation that you can do at the end. So you can just transform these Stateflow charts into C code with just a few clicks. And we also give you a lot of the tools to do all the simulation, testing, verification, and validation before you end up in code, or even during simulation. So those are some of the benefits of Stateflow.
Yeah. And then there's one more question on how to model an electric microgrid. I think that's out of the scope of this particular webinar, but I highly recommend you go take a look at the Simscape documentation, which has got a bunch of information on modeling electric grids and stuff like that. All right, so I think we're ready to move on to our second demo for the day. As soon as you guys can see my screen on the stream. All right, so for today's example, what we're going to take a look at is we're going to look at a simple quadcopter and how we could fly a quadcopter using Stateflow to govern the sort of decision logic of it. Okay, so I'm going to pull up. This is a Simscape. What you can see on the screen is a Simscape or a similar 3D animation visualization of this Parrot mini drone quadcopter that we're flying. If you look at our Simulink model over here, it's got a bunch. This is the plant model. It contains the dynamics of the quadcopter. That's not what we're interested in today. We're going to go into the flight control system and take a look at our control system. And for the person that asked the question about using Stateflow in your controllers, this is a good example of how you could use Stateflow to do the high-level control. So as you can see, this controller block that we've got here on screen, this essentially has your position, altitude in your controller. We're not going to touch that at all. They're just PIDs implemented under the hood. We're going to go into this path planning state that we have here, or path planning subsystem. Now, if you look at the path planning subsystem, we've got a bunch of data coming in from the state estimator. Again, this is a very simplified model. We're not going to really touch that a whole lot. We're just going to think of it as doing some sort of dead reckoning, where we ask the drone to take off, sort of move around until it sees a blue color square on the ground, and we're going to use this this information coming in from our vision-based data. So if we go up a couple levels, there's an image processing system that's doing a simple color thresholding algorithm to identify the blue color, right? So that system will give us a flag, if you will, saying, okay, I've seen something that's blue. What we're going to do is we're going to go in and use Stateflow to actually tell the drone to move through its different states, right? So as Ed did earlier in Simulink Online, I'm using the Simulink desktop version. Just because there are some aspects of Simulink that are not supported in online yet, especially things like the like the visualizations and stuff like that. So that's why we're in the in Simulink desktop, if you will. So I'm going to go ahead and grab a Stateflow chart real quick. Just use the quick insert. Now, in this Stateflow chart, we essentially our system's going to run through 3 states, right, Ed? If you want to take off, fly around for a little bit, and then land, we essentially need 3 states. So let's call the first guy takeoff. Remember, you have to name your states, otherwise it'll error out. So it's a good practice. The first time you drag a state in is just give it a name. You can right-click and drag to make a copy of it. And Stateflow is smart enough to tell me that it's take on. I don't think it's take. I don't think we want to call it take on, but Stateflow is sometimes smart enough. So if you put in like an off state, it'll know that your next state is going to be an on state. So it'll sort of help you with that. But let's call this state go right, because we know, again, we're doing a very simple dead reckoning over here. We know that the blue block is to the right of our starting position. And then I'm going to copy this and make a third state, and we're going to call this, ooh, go wrong. I like that. Don't you like it when Simulink makes suggestions to you?
I love this. And one of the nice things about Stateflow is that it uses edit time checking. So it does a pretty good job letting you know, giving you warnings and errors if the thing is not going to compile and run. But I love these suggestions that it's giving you.
That's awesome. So let's call this the land state. All right. Now, again, we'd have to go in and set some actions, right? So actions and transitions. So in the takeoff state, all of our actions are going to be during actions. So I'm just going to call it du. And then what we want to do is, again, now this is not this logic is not controlling the commands that go out to the motors. It's controlling what goes into your controller, right? So the way our model is set up is I can use my Stateflow chart to just give it X, Y, Z positions. And my controller is smart enough to sort of handle that and adjust the right motor voltages and stuff like that to make the drone fly there. So in the takeoff state, obviously, I'm going to say X equals 0. That's definitely one action that we want. Y equals 0, which was the other one. So we know that it's going to be at the origin. And then we want to give we want to give it some displacement in the Z direction. Now, the convention with Simulink is negative is upwards, especially with the aerospace block set. So we say Z equals -1.1, and we just wanted to basically take off to a height of 1.1 units above the ground. Okay, so we've got our takeoff state in place. Now let's drop some transitions, and I'm going to show you something really cool with Stateflow. So what we saw in Ed's example was Ed was using sort of Boolean conditional statements, right? You can also model things like temporal logic with Stateflow. So if you want to essentially have some sort of a time buffer between how you'd move from one state to the other, it's actually really simple. You can so as you remember, square brackets indicate a condition. So square brackets, and then you just say after after, and then you open up the brackets and say, let's say 2 seconds, but you can also do something like 2 ticks, 2 minutes, to whatever. Okay, So this is essentially just a simple temporal logic. It's going to say once it enters the takeoff state, wait for 2 seconds, and then move on to the go right state. So what we're doing is we're saying, okay, drone take off and then hover for a little bit so you can stabilize before you start making any motions to the right or the left. Okay, so again with the go right, we're going to have a during condition again over here, and in this condition we wanted to move in the right direction, so the positive y. So let's just use y equals y plus, and let's just give it some small nominal value. So it'll move smoothly rather than just jumping through what it has to do. So this is our go right state. We know that we wanted to sort of keep moving on until our downward facing camera and our vision system sees that blue box, right? So this is where we're going to use information coming from as an input. Now, let me go and drop the connection of, oops. Nope, that's not what it is. let me drop the connection. We want to have another condition here, obviously. And again, these are the three sort of constructs that we spoke about earlier: the events, conditions, and actions. Actions are always within curly braces if they're on a transition. But let's go into this condition and let's call this is blue. And this is interesting because is blue is essentially a flag that's coming in from my vision system. So that could just be my transition. Is blue, is it positive or is it negative? Is it true or is it false rather? So if I go up a level, let me grab this connection here and just drag it into the block. So now this is my is blue condition that's coming in. And then I can also go and connect these up. So let's actually go back in here and complete this before we connect that up. So in the land state, again, du, we're just going to set z equals z plus, let's do 0.01. Now again, remember it's plus because our sign convention is negative in the upward direction. Okay. Let's go into the modeling tab real quick and open up the symbols pane so we can resolve our symbols. So obviously it's telling us that it doesn't know what all of these are. So let's call this an input. Let's delete this guy. Okay, so is blue is the input, and we know that X, Y, and Z are going to be our outputs, which we'll send to which are going to send outside of. So we're going to send outside the stateflow chart. So this is resolved to an output. Let's call this an output as well. Resolve this guy to an output.
Yeah, and we can do this manually, or sometimes when you already have the connections for the input and output, it's smart enough to realize what's an input and what's an output. So that's another way to go about it. Now, if you look at, I'm glad you brought up the point about the temporal logic, so the after that you see in the first condition, because this is a really powerful concept. If you try to imagine implementing temporal logic with code, there's a bunch of things that you have to keep track of. As you write that textual code, whereas here is just one line of code. And the nice thing is that you can combine operational logic, right? Like something that you have on the right, logic. So operational and temporal logic is just gives you a lot of flexibility and a lot of power with just.
And then we've got the numbers are kind of wonky, but X, Y, Z. There we go.
You can probably resize that a little bit.
Yep, let's do that. I'm sure there are a bunch of Simulink power users out there that hate that my signals are crossing, but that's the perils of doing live demos, right? I promise I'll clean this up if I'm publishing this. Anyway, let's actually pull up the visualization so we can see what's happening in here. So this is our stateflow chart. I'm just going to go and grab visualizer. Let me just resize this a little bit so we can see what's happening. And then we can also view what our camera is seeing. So it'll pop up once we actually run this. So I'm going to go ahead and I've set the pacing on for this. I'm going to go and run this system, and you should see how the drone takes off and then sort of hovers. Oh, so you see it's starting from that 0, 0 position.
Yeah.
And
there we go.
This is what the downward camera on the drone is seeing. And you see it'll hover. It sees that green, the blue block, and then lands. And then I just have a flag that's saying, hey, stop the simulation when it lands.
So can we run that again from here? I want to see sort of the progression of the different states and things like that.
Yeah. So I think one good way to visualize this is let's open up this guy here, and now let's run this. So essentially, what we know is when we start running the simulation, it'll get into the takeoff state, sort of hover up to that 1.1 unit mark, and that's when you should start seeing that red strip sort of come into view. And then now we know that it moves to the go right, where it'll sort of hover to the right, and then
there we go.
Switch and land. But yeah, that's essentially a quick introduction of how you can use stateflow as a high level logic. Now, obviously, in this case, we're just using dead reckoning, right? We're just telling it, move forward for a certain time or for a particular amount of time. You can just as well grab information from the state estimator and sort of compare values with that. So say, okay, if the state estimator has moved so much, only then switch states and things like that. So there's a lot that you can do. This is just a quick example of how you can use stateflow for decision logic. Now, do we want to stop and take some questions before we move on to another demo?
Let's do that. I actually have a couple of questions.
Sure.
So if you go over to the debug tab, what are some of the ways that you have to debug state machines, right? As you start adding complexity, because I just thought of that as I saw the error. I know it's an assertion, but you may run into other errors as you develop this logic, and so maybe it's worth going through some of these options
for sure.
Debugging.
So if you're a MATLAB users or Simulink users, you're all familiar with the concept of breakpoints, right? So breakpoints are one really nice way of sort of debugging the state. I think the first debugging method is actually visualizing how the states light up. Like for me, if I understand how my stateflow chart needs to work, as soon as I run it the first time, I'll try and introduce different conditions to make sure that it's actually making all those transitions correctly and visually, or visually debugging the charts, right? Visualizely, that's not a word.
It is
visually debugging the charts. But you can also do something more concrete, like adding a breakpoint. So let's say if you want to add a breakpoint to the go right state, you can right click on the state and say set breakpoint. And what you see is this little red dot that comes here. It's if you've written a lot of MATLAB code, you know what that breakpoint does. So if we run this guy real quick, you'll see what this does. It'll essentially stop the code once it gets into that state. See that it takes off, and then now it said, okay,
there we go.
Code stop, and then you can use, if you want to make sure if your code's actually performing correctly, you can sort of do steps. Where you say step forward 1.
Yep, and that gives you a chance to sort of slow down and inspect the behavior of the state
correct.
machine to make sure it's what you actually would hope would happen. Just like MATLAB code and breakpoint. So it's really powerful to have this. With stateflow.
This is one way of doing it. Do you want to talk about some other ways of debugging stateflow charts, or have we covered all of it?
No, there's plenty. I mean, I don't think we're going to go through all of them in the debugger, but one of the ones that I want to point out right now is grayed out, but it's the activity profiler. And so that gives you a report after you run the simulation of where are the states where you're spending the most time, right? And so we probably don't have to run it, but that's another really good option that we added recently, and it's a really powerful way to debug state charts.
That's awesome. All right,
and you can always log the outputs and things like that for analysis, but we probably want to move on. So let's take a few other questions. There was a question that might be a very good segue for the next demo, and the question was about parallel states. So can we talk more about that, Connell?
Right on
what
time.
are parallel states, and what kind of logic can you do with Stateflow? Can it only be sequential logic, or can you do parallel logic as well?
Perfect. So in fact, it's the perfect segue into what we're going to talk about next. So the essentially what a parallel state is. So the states that we've been looking at so far are sequential, right? Where you follow a default transition, it enters one state, it executes whatever it has to execute within that state, but it's also looking for transitions to move out at the same time. A parallel state essentially means that there are two states that are awake and listening for information at the same time. So let's take a look at this model. This is an automatic gear transmission controller. And essentially what's going to happen is you have to decide two things with an automatic gear controller. Basically what speed range you're in, and then when you cross that particular threshold, do you have to move in the upward direction or the down, do you have to upshift or downshift, right? Those are essentially two things that you're thinking about when you're trying to model an automatic transmission. So let's take a look at the state. Oops, and I have a third state here. I don't know why. All right, cool. So these are what's called parallel states. You can sort of denote a parallel state by noticing this dashed border around it. And then you have a number associated with the hierarchy. So this is the first parallel state. This is the second parallel state, right? Now what's going to happen is as soon as this chart wakes up, both these states are going to be active at the same time. And you'll see it when I run the model. What we're doing here is we're essentially saying, okay, so in the first state, let's pick which gear we want to be in, whether we want to be in first gear, second gear, or third gear, right? And then the second state is what we like to call the selection state, where you're either in a steady state mode where you're not shifting any gears, or you cross some threshold within that gear range that you want to upshift and go to a higher gear, or downshift and go to a lower gear, right? And so the way we're going to compute this threshold is we're using what's called a simulating function. Now this really expands Stateflow because you can use things like simulating functions, MATLAB functions, graphical functions, truth tables, etc. And all of those are visible on this this left-hand tool strip. But if you open up the simulating function, what you have in here is essentially just a couple of lookup tables. So based on throttle position and gear value, it'll sort of tell you what your thresholds are. It's just a lookup table. This could very well be PID controllers or whatever state, whatever simulating models that you have. I think one good way of looking at this is if you've got, say, a vehicle that has two modes of operation. One is position control and one is velocity control. You can sort of use Stateflow to control that and sort of pick which controller is being used at any point in time. Right.
Yep.
Okay.
And so I think another powerful concept is the idea of reuse, right? So if you have these subsystems or MATLAB functions, you don't have to recreate all of that. You just make a function and then you call it as much as you need to. And there's a couple of other points I want to highlight here with the simulating function. You notice that the syntax that you have in the box is pretty similar to MATLAB syntax, right? You have the function outputs, the function call, and then the inputs to the function. And so that brings me to my other point, which is the action language for these charts. Usually you can have MATLAB as the action language for these charts. That makes it really intuitive. So it's like you're using MATLAB code in Stateflow for all the syntax, or you can have C action language for the chart. And you can actually see that in the little bottom left corner icon there. It shows you what the action language is for that chart. Looks like it's C for this one, right?
All right, so let's introduce the concept of events. I know we spoke about events a little earlier, but if you're in a simulating, or if you're in a Stateflow chart and you see something with this gold orange text color, that's what's called an event, right? So essentially, what we're saying is if you look at this particular area, right, where if you look at the selection state, this chart will start by entering the steady state. When your vehicle speed goes below this this threshold that we've computed using the Simulink function, it'll go into what's called the downshifting stage, the downshifting state rather. Now, once it goes into the downshifting state, we're going to use this after, and then t wait is just it's just a local parameter. This could be 5, it could be whatever, it just could be a number. We're saying after some amount of ticks, if your vehicle speed, and notice the square brackets indicating that this is a condition. So if the vehicle speed is less than or equal to that same down threshold value, let's trigger this event. So the way you trigger an event is you say gear_state, which is the name of this big state up here, and then you call that event dot, and then you call the event after that. So you say gear_state dot down. Now what's going to happen is as soon as this action gets called, depending on which state we're in, it'll take the transition that is triggered by that is guarded by that down event, right? So that's essentially how events work at a very high level. So we can actually go ahead and run this code real quick, and we can see how this works. Let me actually open up the results tab as well and pull that in here. Just give me a second.
Yep. And so as you run this, one of the things that I want to point your attention to again, because Connell covered it, is when you look at those transitions down at the bottom, right? You see you're combining temporal logic with the conditions and then actions, right, to trigger the event. So if you look at the square braces, the curly braces, you get the power of it all in just one transition line. So
yep.
That's really nice.
If we go ahead and run this, we should see that these engine, if you're an automotive person and you know what it means, typically a drop in engine RPM is when you shift your gear. So let's actually see what happens, and we'll watch it sort of switch through. You saw that blip and the state change. So we're doing a little bit of upshifting. We made a sort of in steady state, and then now we're going to downshift, and you see that the RPMs will increase. But yeah, this is a sort of notice that when you have parallel states, both the states are active. They're both sort of highlighted and listening for information at the same time. I think one good use case of parallel states is, say if you have like some vehicle that's doing something, and you have like a telemetry system where you can update missions to that vehicle, if you will. Your communication layer could be a parallel state that's also listening at the same time as the other state's running, and then whenever you upload a new mission from your ground station, it'll that parallel state will change some parameters that can actually change the way your system's operating. So that's just one example of how you could use parallel states. This is another one. But yeah, this is at a high level how you can go through Stateflow.
Yeah, this is pretty awesome. Pretty good overview. And again, just to recap, we saw the 3 demos. So the charge balancing logic, then we went into the drone logic, and another real world example of how you could implement an automatic transition with temporal logic, events, and so on. Connell, any other things we want to cover here before we move to the third section on resources and getting started?
I think let's see if there are any questions based on what we've done so far. Let's give it like a couple minutes of questions, then we can go back to while they're setting up our screens in the back to go through our last section. Let's try and cover up. Let's try and answer any questions that y'all have. So please pop them in the chat.
So I see a question coming in about how to transfer data between 2 parallel states in the Stateflow.
So technically, both of these states are viewing the same base workspace under the hood. So so you don't really need to, that's how data's, they can both see the same data variables. If you want to send, like for example, in this case, we've used to sort of send this this event. We're not technically sending an event. We're just triggering an event value, and then because both of these states are looking at the same base workspace or the same workspace under the hood, they know when these values get updated. So hopefully that answers your question.
Right, and you showed another example with the event, right, where when you triggered the event, you had the state name and then also the event name to trigger that. So, but yes, I think the right answer is what you said. They're looking at the same local data or data repository, so they would know when a parameter has changed and it can work with that value. Can we create a test case list to see if the control logic fails in any condition or not? That's an excellent question. And so, yes, we give you the tools to verify and validate the design, right? And so testing or simulation is a form of testing. You can wrap your logic in a test harness to sort of work with predetermined inputs, analyze the outputs, or you can use simulating test and create a test suite where you go through different scenarios, different inputs, and you can even automate the process of testing. And then you get nice reports that you can share with colleagues and other groups. And you can even do things like coverage, but those are more sophisticated topics that we can cover in different live streams.
Yep. How do we reduce cyclomatic complexity? I'm not sure I'm familiar what that means. I'm learning new words today. Let's do what all engineers do and Google what that means.
I've heard the term before. I think it has. I'm not a computer scientist, so maybe I'll just.
Me either.
I'll Google it too.
Cyclomatic complexity.
All right. While you Google that, can you give us one or more examples for parallel and or? Well, you can. I think we shared in the chat the example that Connell was working with for the automatic transmission that has parallel states. Also, the first demo that I showed you for the cell balancing logic, that's an isolated component of a much larger system where we have a closed loop model of a BMS, a battery management system, and the plant for the battery itself. And so there we have the supervisory logic for that, and it has parallel states and fault detection, and you can see basically the full power of Stateflow on that one as well. So I recommend you to check out those links. And I can talk about examples in just a few minutes here.
Okay, so maybe this is, I'm going to try and attempt to answer the cyclomatic complexity question and the question that talks about parallel and or states. So, when what we saw are two parallel states. The parallel states are also called, they're also like the or condition states, like both are active at this, or rather and condition states where both are active at the same time. You can also use a concept called superstates and substates. So essentially, if we look at one of the models that we were looking at, we had. Can you pull up that charge balancing model if your screen is?
It's ready to go, so let's do it. Yep, we're working through it.
Sweet. So if everyone can see can see the screen that's going on, so essentially what we've got is we've got a balancing off and a balancing on. Now, both of these could be embedded into what's called a superstate, right? And essentially, once you only get into the superstate, or these smaller states only become active once you're in the larger superstate. So one good sort of convention and a good modeling practice is to try and use substates and superstates as far as possible, because what will happen is you can sort of collapse this and reuse different parts of this to hopefully reduce your the complexity of having multiple lines and all of these kind of things. But this is an example of an so like I know in this case we've got transitions between these two states, but if these two states aren't connected to each other, that would be an example of an OR state, if you will, right? It would either come in activate one of those or the other one based on which condition it is.
Yep, and just to go over the mechanics here is how you can change that chart decomposition, right, to be exclusive or parallel, which is exactly what you're talking about. So just go to the modeling tab, and you can play with that for the different states in your chart.
Yeah, so I think in terms of cyclomatic complexity, you want to use these sort of superstate substates, kind of like how you use subsystems in Simulink. But yeah, hopefully this answers your question.
All right, so
that as a non-computer scientist.
So we've covered a pretty good amount of ground. Let's go into the last question, or the last section that we had for today, and that is, how do you get started with Stateflow? And so I want to show you a couple of ways for that. I want to go back to the Simulink start page. So when you open up Simulink, you can actually see this examples tab, and this is something that we have mentioned before in our previous live streams. So you can check out modeling an automatic transmission. So that's how you can access the one that you were working with, Connell. There's a bunch of others for Simulink and other products. And down here, we have some for Stateflow. So you can see the featured ones here. And if you want to see all the examples available to you, you can also click on the view all, and that'll take you to that page. So you can run those examples, modify them, tweak them, and try to fit them to your custom needs. So that's one way. The other way I want to point you, or that I want to show you, is with the on-ramps. And these on-ramps are, again, free interactive tutorials that help you get started and familiar with the tools in just a couple of hours. So we have them for Simulink, Stateflow, Simscape, Control Design, and they work with Simulink Online. So if we look at the Stateflow on-ramp, it sort of gives you a curriculum or a set of activities here. And if we open, for example, this task or this section on running state machines, we'll see it'll bring up the interface, and it has different panes to basically walk you through the exercises. So now if I maximize that, this is pretty nice. And so what you see here is, to the left, I have the tasks and all the instructions that I have to follow. Here I have, my working area with the Stateflow or Simulink canvas. And then here I have things like the results and also the symbols pane. So, and you can submit and progress through, and you get immediate feedback on how you're doing with these on-ramps. So definitely encourage you to check that out. You can also just Google it, and that'll take you to the Stateflow or the Simulink on-ramp page. We have pages for that, and you can get started that way. And so we've covered examples, on-ramps, and then the last thing I would like to mention is the community. We have a pretty strong community, and I think many of the viewers are part of that community, so thank you for that. So if you go to MATLAB Central here, you can look at answers provided by MathWorks experts, but also the community, and then file exchange, when you can download the work of other people with MATLAB, Simulink, and all the other products. So that's what I wanted to point you to. With that, I think maybe, well, we're run out of time,
questions,
but we can take a few questions and then wrap up after that.
For stateflow analysis, can I use a Simulink model? I'm not sure what you mean by that question, but yes, you can. I mean, essentially all that we've done today is we've been working within Simulink models, but they just launched a feature called Stateflow for MATLAB. So you can essentially, build a Stateflow chart, but then if you want to test it, call it from MATLAB and sort of give it like test cases and things like that. So that's you can use it with both, with Simulink and with MATLAB.
Yep, and also to complement that answer, you can actually log state outputs with in your Simulink model to basically do some graphical analysis of the behavior of your state charts. All right. Anything else?
All right. So I think I don't see any more questions coming in. Thank you all of y'all for taking the time out to listen to us talk about Stateflow. Yeah, please hit us up in the comments and let us know what more you'd like us to talk about. There are, I know we've got a lot of requests for programming hardware, and we promise you that we're going to do one at some point in the future. But yes, if you have any topics to talk about, please let us know in the comments, and hit that subscribe button so you know that you can find us again when we go live.
And the notification bell so that you know when we release new content.
Yep. Smash that like button.
All right, folks. Thank you very much for your time and your attention. This was great. Thank you, Connell.
Thanks, Ed.